acid strength. Hopefully you remember from previous studies, we're talking about weak electrolytes and strong electrolytes. A strong electrolyte conducts electricity well, a weak electrolyte does not conduct electricity well, and a non-electrolyte does not conduct electricity at all. The strength of the electrolyte depends on the extent of its dissociation into ions. So you can make a strong electrolyte solution using sodium chloride. Sodium chloride dissolves in water, and when it does, it dissociates completely into ions, and there are no sodium chloride formula units or particles left. Sugar, on the other hand, which is also very soluble in water, does not form ions in water, and so it is a non-electrolyte. So we have the same sort of criteria for the strength of an acid. It's going to depend on this equilibrium. This is representing a generic acid. Here's the hydrogen that is given off when it gets into water, and then A is just the anion. There is no element A, just like there's no element X. We use both of them as stand-ins for other things. So HA, you put it in water, and it forms hydronium ion, and then what's left is this A minus. So this is the acid. It's donating a proton to the water. The water's acting as a base. Then we get hydronium ion. This is the conjugate acid. This is the conjugate base of this initial acid. So a strong acid completely ionizes in solution, completely forms ions. A weak acid only partially ionizes. Okay? So, strong acids first. There are 6 important strong acids. Just memorize them. And then if it's not one of the 6, it must be a weak acid. So that's not too bad. There's 6 of them, and these are, familiar acids: hydrochloric, hydrobromic, hydroiodic acid, and then the 3 of the oxyacids: nitric, perchloric, and sulfuric acid. Now, we sometimes use these words monoprotic, diprotic, and triprotic when we refer to acids, and that refers to the number of ionizable protons that are in the acid. So if we look at the formula for HCl, there's only 1 hydrogen there. It can only give out 1 hydrogen ion per molecule. But H2SO4 has 2 hydrogens, and they are both ionizable. Okay? We're going to study more about the diprotic and the triprotic ones later because, like for sulfuric acid, the first one that comes off is strong and the second one's weak. So that's kind of complicated, but it's still classified as a strong acid. So diprotic, 2 ionizable protons, and triprotic, 3. So looking at hydrochloric acid. You put HCl in water. Here we have a single arrow. This is indicating that there's complete ionization. And it goes to hydronium ions and chloride ions, and there's essentially no HCl left. No hydrogen chloride molecules are left. And that's what makes it a strong acid. It ionizes completely. There's a picture, if you like pictures. And so here we put HCl in here. Here we're representing it with letters. And we've got hydronium ions and we've got chloride ions. There's no HCl in the solution. Here we've got it with little pictures. There's the HCl. The little white hydrogen balls come off and stick onto the water. The green chlorides are left. There are none of these in the solution. So that makes dealing with the concentration of a strong acid solution easy because if you have a 1 molar HCl solution, the hydronium ion concentration is going to be 1 molar. Because all of the hydrogens, you had 1 mole per liter of this HCl. It all came apart, so it makes 1 mole per liter of this and 1 mole per liter of that. Yes?
How do I ask this? So HCl goes, if it wasn't for the water, it would be less dangerous? Is it the hydronium ion that becomes the dangerous part of it?
That's a good question. Would HCl be less dangerous if it wasn't in water? That's a good question. I'll think my way through it here. HCl is a covalent compound, and it's a gas under normal conditions. So it depends on how you define dangerous, right? Okay, so it's a gas. That means you could inhale it. What is in your lungs? Water, right? So you inhale HCl, it comes in contact with the water in the mucus layer in your lungs, and there you've got acid. So in that sense, it's more dangerous because you're probably not going to be snorting a 1 molar HCl solution, right? You could breathe it. You could try, but most people don't. Accidental inhalation of a gas is much more common than accidental inhalation of liquid.
Would it be more dangerous if you were to expose your skin, like part of your arm, to the gas or to the aqueous solution?
You know, I can't really I can't really comment on that. You know, it might depend on how dry your skin is, right?
Yeah.
I have really dry skin, so maybe I'd be okay, but somebody who's all sweaty, you know, they might have a problem. I don't know. Those are good questions.
Ask a biologist.
We could ask a biologist. Or we could look it up. Okay, so Randy wants to try it. Let's talk about weak acids. And these words can be deceptive because we see strong acid, we think, ooh, dangerous, right? Weak acid, oh, well, that's benign, that's relatively safe. No, not necessarily. The weak and the strong just talk about how much they dissociate, how much they ionize. So if we have an HF solution, hydrofluoric acid is a weak acid. So when we write the equation for it reacting with water, we have an equilibrium here, equilibrium arrow, and that indicates that there's partial ionization. If we look at the picture down here, you put HF in water, most of what's there is going to be intact hydrogen fluoride molecules. It will form some hydronium ions. It will donate protons, but it doesn't do so to a large extent. It's a small extent. And so here we see the same thing over here. We have some hydronium ions formed, and we have some fluoride ions, but we also have a lot of the intact molecules. So then when we think about, well, what's the concentration of the two ions that are formed from HF, we can't, with just this information, we can't really say more than saying that the hydronium ion concentration is less than the concentration of the acid itself, because it ionizes partially. And maybe if, you know, what have we been talking about in chapter 14? Great facial expression there. He has no clue. He's teasing. We were talking about equilibria, right? And equilibrium constants. And so can you see how maybe an equilibrium constant might be helpful in predicting what's going to happen with these weak acids? That's where we're going. Well, why do some acids ionize completely and others don't? It has to do with the strength of the attraction between the conjugate base and that proton, the hydrogen ion. If there is a weak attraction, if these guys are like, yeah, we kind of like each other, but I like the water molecule, they're going to just separate, okay? And here, the attraction in the weak acid, the attraction between the hydrogen ion and the conjugate base is stronger, and so more of them are going to stay together. Have I talked to you about the party analogy with double displacement reactions? I don't think I have. Some of my 1A students are familiar with this. So it just occurs to me that this applies here. So in chemistry land, anions are feminine and cations are masculine. hydrogen is kind of a wimpy guy because he's not really a metal. Most of these are metals, but it'll work. So these guys are attracted to each other, right? We've got positive charge, we've got negative charge. There's an attraction there. But they go to a party. The party is the beaker of water, okay? So if you go to the party, the guy and the girl, and the attraction between you is pretty weak. Get to the party, there's all these interesting people around. You're probably not going to stay right next to each other the whole party, right? You're going to mingle and see who else is there, right? The precipitation, which is not what we're talking about right now, the precipitation, like if this was chloride, the precipitation would be she runs into a silver ion, and he is mighty fine. And they like each other so much that they precipitate and they go sit on the couch on the back porch and neck for the rest of the party, right? But we're not precipitating here. But in this strong acid, the attraction between these is weak. You put them in water, they split up. They go looking for other things. A weak acid, though, these guys are really attracted to each other. And so they go to the party, and a lot of those molecules are going to stay together. I guess you could think of this in terms of strong personality and weak personality. Maybe these guys are a little insecure, and they don't know anybody, and so they came with their friend. And I'm just going to stay with you because I'm shy and I don't really feel comfortable going out by myself. And so there's this attraction between them, and they stay together. That's what weak acids do. Strong acids, they split. Question?
So I'm assuming like when the acids and water, like there's a lot more water molecules.
There's a lot more water molecules than acid.
Okay, so I don't see why some should ionize and some shouldn't, because they're all the same molecule, and I mean like the bonds are.
Well, it's not that the water is ionizing, it's that the acid is ionizing.
So,
Because,
but you said
like if you've got HF is a weak acid. So hydrogen and fluoride, but HCl is a strong acid. Well, just looking at those two and comparing fluoride and chloride on the periodic table, which one's more electronegative? Fluorine. And so just based on their positions in the periodic table, we might be able to decide that there's a stronger attraction between hydrogen and fluoride than there is between hydrogen and chloride.
Okay, so
You cannot wholesale go and do that looking at all of them, though. It's a lot more complicated.
So in the HF one,
Mm-hmm.
some of them do ionize though.
Some
so
do.
What's the scenario where some ionize, some don't? Like what makes these ones ionize as opposed to these ones not?
Well, it's an equilibrium. And so it's going in both directions. So it'll ionize and then change its mind. And so it's going back and forth and back and forth.
So you think like they all do, and it's like go right back.
Yeah.
So effectively, it's some don't.
Right. So, they'll separate, but as soon as they see another of that kind, they're going to get back together again. Maybe you could think of it that way. But the equilibrium constant is what tells us how far to one side or the other that equilibrium lies. It's a good question. When you can really, in your mind, have it clear and see what's going on with this stuff, it's not that hard. There's some tricky stuff with the math. You got to be careful with some things. But conceptually, this is not like trying to understand quantum mechanics or something, right? So. No, that's these guys, if we're going to go with that, these are strong individuals, and so they're very comfortable going out on their own. Mingling at a party. They don't know anybody, but they're just going to head out and meet people. And these guys are weak, and they're shy, and they don't feel comfortable being in a crowd by themselves. And so they're going to stick with their partner that they came with. I'm making this up just right now. So sometimes it doesn't come out so good. But the implication of this is the stronger the acid, the weaker the conjugate base. So in this equilibrium, here we have an acid and a conjugate base. I have to change colors from what I did in Tulare yesterday. So here's our acid. And which one's the conjugate base?
Conjugate base.
The conjugate base. The conjugate base differs from the acid by an H+.
Oh, by an H+? So it's a hydronium.
It's the A-. Because this, when this does the acid thing and donates a proton, it becomes this. Okay? And this is acting as a base. When it does the base thing and accepts a proton, it becomes this.
Yep.
So this is the base, this is the conjugate acid. But we're just going to look at the acid and the conjugate base. So in a weak acid, the equilibrium might actually be a little farther that way. Well, it is going to be farther that way. It's not going to be even. There's going to be more of the acid and less of the conjugate base. So if we're looking at this as a base, trying to accept hydrogen ions, is it going to be very good at that? This conjugate base. This is a weak acid. So we're talking about weak acid right now.
There's a weak attraction, right? So
in this equilibrium, it lies mostly to this side. The HA is favored over the A-. So if we're focusing on the A-, is it going to want to stay this way or is it going to want to go over there? It's going to want to go over here. So this is going to be a fairly strong base. A strong base will attract the hydrogen ions. And it will ionize when it does that, right? If we look at this, well, never mind. I'm getting off the track. Okay, so scratch that, and let's talk about a strong acid. Strong acid goes all the way. There's none of this left, and it all goes to A-. So then if you're looking at A- as a base, being a proton acceptor, is the reaction going to go to the left at all? No, it isn't. This is not going to be real good at acting as a base. So if we have a strong acid, we have a weak base. If we have a weak acid, we have a strong base. And so they go up and down. They're inversely related. Did that make any sense? Some people don't. Perfect sense, thank you. You're just trying to get in good. Pardon me?
I got it, and you started explaining, and I started getting confused.
Yeah, that's what happens sometimes. So just stick with the first part that you did understand. Okay, so the acid ionization constant, which I meant to bold, but I forgot to bold, so I'll highlight it instead. This should be bolded, because we need to know what that is. The acid ionization constant, Ka. So we've talked about Kp and Kc. This is an equilibrium constant for an acid. It's for the ionization of a weak acid. So here's our generic acid reaction. And if we were to write an equilibrium constant for this, we would have the concentration of the hydronium times the concentration of A- divided by the concentration of the acid. Why do we leave the H2O out? It's a liquid and its concentration can't change. This is a simpler way to represent the same thing, where we're pretending, we're ignoring the fact that this hydrogen is actually piggybacking on a water molecule. It's a lot simpler to write it this way, so I like to do it this way. We have HA just coming apart into H plus and A minus. And so then we would write it like this. These two equations represent exactly the same thing. These two expressions represent exactly the same thing. One is just kind of a cheat. It's just a shortcut. It's like, well, yeah, we know there's water in there. Why do we have to draw it all the time? So if we have a smaller Ka, that means the concentrations of products are smaller relative to the reactants, right? And so the reaction is going to, the equilibrium is going to favor this side. That's a weaker acid. If you have a stronger acid, Ka would be larger, more products, and so a strong acid is going to have a larger Ka. So small Ka, less ionization, weaker acid. So we can look at the Kas and compare the strength of the acids. Let's do that right now. So here are some acid ionization constants, and they're giving you the structural formula and the ionization reactions and the Kas. The structural formula can be helpful because it's not always obvious from just the regular formula, the molecular formula, what that hydrogen is attached to. And with some of them, like here, benzoic acid has 6 hydrogens, but only one of them is ionizable. The hydrogens, where did my pointer go? The hydrogens attached to the carbons on the ring are not going to go anywhere. Only this hydrogen attached to this carboxyl group is going to go anywhere. And the same thing with acetic acid. So here's the equilibrium reaction for this, and here's the Ka. So which one of these is the strongest of these weak acids? The strongest. The top one, right? The chlorous acid. Larger Ka, more product, stronger acid. And so then the weakest one is going to be down here at the bottom, phenol. Phenol is an acid, but it's a very weak acid. 10 to the minus 10. That's pretty small. You might need to refer to this table when you're doing homework because they might not hand you the Ka on a silver platter.